Unit 4 nodes, day 2. This is section 7.5 in your book. We're jumping around a little bit, talking about different ways to integrate. Now we are talking about integration by using partial fraction decomposition. So back in Unit 1, we reviewed how to do partial fraction decomposition. And the reason we did that was because you're going to have to integrate by first doing that. So example 1 gives us the integral of 4x plus 10 over x squared plus 5x plus 6 dx. I would always start by using some of the techniques we learned last year. So if you were given this problem last year, you almost certainly would have started by making u equal to x squared plus 5x plus 6. Hopefully that's what you did, right? And then our du is 2x plus 5 dx. And this problem is set up so that if I factor this, I have that 2x plus 5 dx is in my problem. I can take out that 2. There's 2x plus 5 dx. That becomes du. So I get the integral of 2 over u, which integrates to 2 ln of the absolute value of u. So we have 2 times natural log of the absolute value of x squared plus 5x plus 6 plus c. So if it can be done by u substitution, it's going to be much faster and easier to do it that way. You would get the same answer, or an equivalent answer. It might not look exactly like that. Let's try another one here. This one says we have the integral of 4x plus 12 over x squared plus 5x plus 6. Looks very similar. Again, the first thing you might try to do is make u equal to the bottom. The problem is du is 2x plus 5, and even if I take a 2 out of the top here, I'm not going to get 2x plus 5. I got 2x plus 6 there. So the next thing we might try to do is factor. I can take a 4 out of the top. And on the bottom, I have x plus 2 times x plus 3. So we can simplify this. And now it's again something we can use substitute with. So we get the integral of 4 over u, which is 4 ln of u. So we get 4 times the natural log of the absolute value of x plus 2 plus c. Again, much faster than it would be if you tried to use partial fractions on that problem. Example 3. Looks almost identical. The integral of 4x plus 14 this time over x squared plus 5x plus 6 dx. So maybe you would consider making u equal to the bottom, but again, even if I factor out a 2, I don't have the 2x plus 5 on the top. I could factor a 2 out of the numerator, but it's not going to cancel with anything on the bottom this time. I'd have 2 times 2x plus 7. X plus 2 and x plus 3, nothing cancels there. So we are out of other ways to do this. So when that's the case, we are going to need to use partial fractions. So what we're doing is we're going to rewrite the integrand. Don't worry about the dx, don't worry about the integral sign, but we want to write 4x plus 14 over, factor this, x plus 2, x plus 3, and we want to write it as its partial fractions. A over x plus 2 plus b over x plus 3. And do the partial fractions the same way we did before. We're going to multiply both sides by x plus 2 times x plus 3. So if I multiply this side by that, they're going to cancel. So I get 4x plus 14 equals a When I distribute both of these to this, the x plus 2's cancel. So I get times x plus 3. And then the same thing here. When I distribute this, the x plus 3's cancel. So I get x plus 2. And now we plug in a value for x. We want to choose -3 because that'll make this 0. So if I plug in -3, this part becomes 0. I get -1b equals -12 plus 14. B is -2. And then if I choose x equals -2, because that makes this 0, I get 1a equals -8 plus 14. So this here, I started with this, and that is the same thing as 6 over x plus 2 minus 2 over x plus 3. So this guy here is the same as that, so I can rewrite my problem so that it says this instead. And now we integrate this. Again, technically you are substituting here. So we get 6 ln of u. U is x plus 2. This works out the same way. Minus 2 ln of the absolute value of x plus 3. And there's our answer. So nothing super new there. We are rewriting with partial fractions, which we've done. And then once we have it in the partial fractions, we're integrating, which we've done. It's just kind of combining the two things. Oh boy, example 4. We have the integral of x cubed plus 5x squared plus 8x plus 11 over x squared plus 4x plus 3. This is an improper fraction if the degree in the numerator is greater than the degree in the denominator. Before you start working with the partial fractions, we want to simplify this. And the way we're going to simplify it is by dividing using long division. So the way we do long division, we want to think about what times x squared gives me x cubed. X squared times x is x cubed. And then I multiply x times each of these. I'm multiplying these two together, but I'm distributing. So x squared times x is x cubed, 4x times x, and 3 times x. And then I subtract. And then I do those steps over again. What times x squared is x squared? 1. Multiply. 1 times 4x. 1 times 3. Subtract. My degree in the remainder here is now less than the degree of what I'm dividing by. So we are finished with the long division part of it. So this is the same thing as x plus 1 plus my remainder over what I divided by. If we try to factor this, factor the bottom, notice nothing cancels. X plus 1, x plus 3. If I try to make u equal to the bottom here, I get 2x plus 4 as my du, which is not going to work with what I have in the numerator here. So the only way to simplify this part here is, again, by using partial fractions. just rewrote the same thing twice there. I don't know why I did that. This I wanted the x plus 3 and x plus 1. So the x plus 1 is on there. We don't need to worry about that much. It's going to be part of it, but this is what I'm working with on my partial fractions. So partial fractions, I've got x plus 8 over x plus 3 times x plus 1. A over x plus 3 and b over x plus 1. Multiply through by that. It's going to give me x plus 8 equals a times x plus 1 plus b times x plus 3. Plug in -1 for my x's. Gives me b is 7/2. Plug in -3. Gives me b is -5/2. So I can rewrite this whole thing right here as x plus 1 plus a over x plus 3, and a is 7/2, minus b over x plus 1. Oops. And don't forget, we're integrating this. And then we can integrate. Integral of x is 1/2 x squared. Integral of 1 is x. As long as this is 1x plus something or 1x minus something, we actually don't need to worry much about the u substitution because du is going to be equal to dx. If it makes you feel better to write it in there, by all means do it. But now if it's 2x plus 3 and the 2's on the inside of the parentheses here, now you're going to want to make sure you use substitute. And there is our very long, very gross answer. 1/2 x plus 7/2 ln of x plus 3 minus 5/2 ln of the absolute value of x plus 1 plus c. Let's take a look at this one. The integral of e to the x over e to the x minus 1 times e to the x minus 3. Doesn't necessarily look like it's a partial fractions problem. We are going to make u equal to e to the x. And that way du is e to the x dx. So when I change everything to u's, there's my du. So I get 1 over u minus 1 times u minus 3. And now hopefully we can see this is a problem where we need to use partial fractions. Multiply through. And we're working with these u's here. I'm going to plug in 3 for u, would give me 2b equals 1. B is 1/2, and plug in 1. A would be -1/2. So a over u minus 1, -1/2 over u minus 1, plus 1/2 over u minus 3. So we get -1/2. Again, it's 1u minus 1 on the bottom, so it would look like this without actually having to do any substitution there. And I don't have any u's in the original problem, so you don't want them in your final answer. Make sure you write it back in terms of x. One last problem I'm going to show you here. We're not going to work all the way through it. Not that one. This one here. Again, it doesn't necessarily look like it's a partial fractions problem. We have the integral of secant squared x over tangent cubed x minus tangent squared x. If we make u equal to tangent x, du would be secant squared x. So there's du. So when I change it all to u's, we get here, and then we can factor. And notice this is the point then when you would jump down into the partial fractions. Notice I've got u squared. So I'm going to write a over u squared plus b over u, and then c over u minus 1. And you could go and find a, B, and C. I don't think we need to practice that a whole lot more. If you are having questions about how to do it from there, let me know and we can talk.